So guys, welcome back to the Raptors. We continue with our series of most expected physics questions, which may turn up tomorrow in your board exam. All right, so we are now on ray optics. From ray optics, there are most of the questions which come are mostly derivations and conceptual questions. There are a few numerical questions which may also turn up. So from derivation points of view, I'll mention the derivations that are important, which one should go through is to prove R equal to 2F. Other derivation is Lensmaker's formula. Third is to find angle of minimum deviation. To find angle of minimum deviation when light passes through a prism. And conceptual questions on TIR, total internal reflection. So the derivation part will be dealt with in another video. I'll share notes, detailed notes of how to derive these things. We'll touch upon the expected questions. Apart from derivation, what expected questions may come up. So yes, you already know the prerequisites of TIR. What are prerequisites?
लाइट जो मस्ट ट्रैवल करती है रेयर टू डेंसर करती है
Light must
सॉरी
travel
डेंसर टू रेयर
from denser to rarer medium. And number two, the angle of incidence
ग्रेटर देन होता है क्रिटिकल एंगल के
must be greater than or equal to the critical angle. That is, theta should be greater than equal to theta c. Now the second part, you see, the second part question says refractive index of water is this. There is a fish, so assume an aquarium. There is a fish here. Fish wants to look outside. Now beyond certain point a critical angle will reach theta c, and then the ray will go just grazing the surface, so rays will travel like this. So the fish will be able to look only in this cone whose semi-vertical angle is theta. Now since the cone is symmetrical, this theta c is this theta c, so we want to find this radius r. Suppose the depth of the water is d, so you know sine theta c is equal to 1 by mu, so it is 1 by 4 by 3, so it will be 3 by 4 sine theta c. Now in this triangle, sine will be, suppose this is OAB. In triangle OAB, sine theta c will be R, OA by OB. So OA is radius r, and then AB is d, depth d. So the radius r will be d into sine theta c, so d into 3 by 4. So the radius or the area of the surface over which the fish can see is 3 by 4 of the depth. All right. The semi-vertical angle, will be just theta c. So theta c can be found out as sine inverse 3 by 4. All right. Right. So another important question regarding angle of minimum deviation through a prism is a ray of light PQ is incident at point Q of the prism and it passes parallel to the face BC. Now it emerges out of another face AC from point R, so that AQ is equal to AR. Now it itself shows that light is parallel to the BC. Now we have to draw a ray diagram, and the angle of prism is given to be 60 degrees and the material of the prism has a refractive index of √3. What we need to find out first, we need to draw a ray diagram, and then angle of incidence we need to find out, and then angle of deviation. Now few important things that you should draw out of this is AQ is equal to AR means ray is parallel to BC. Whenever ray is parallel to BC, it means the deviation angle is minimum. If angle of deviation is minimum, you immediately realize that R1 is equal to R2, which is R, and that is half of the angle of prism. Second relation you should realize is angle of incidence plus angle of emergence is equal to A plus delta minimum. And at angle of minimum deviation, angle of incidence is same as angle of uh, incidence. So you see the diagram looks like this. So this is delta and this is I or E. So when I is equal to E, the angle of deviation is minimum. So to find out angle of incidence, we are going to use Snell's law, because angle of refraction is 30 degrees. So sine of I by sine of R is √3. So sine of I becomes √3 into half, sine 30 is half. So √3 by 2 is sine of I is √3 by 2. So I is 60 degrees. So angle of incidence is 60 degree. That means angle of emergence is also 60 degrees. So we use this relation for at minimum deviation to find angle of minimum deviation. I plus E equal to A plus delta minimum. We put the values 60, 60 equal to 60 plus delta minimum. Angle of deviation also becomes 60 degree. So this question uses the concept of angle of minimum deviation and what happens at angle of minimum deviation. All right. So in this question, it says there is Young's double slit experiment. Slits are separated by 0.5 mm while the screen is placed at 1 meter away. This question says that distance between the fifth bright and then second dark. This is dark fringe and this is bright fringe. The distance between fifth bright and second dark is 4.13 mm, and we have to find the wavelength of the light used. So let us do it. For bright fringe, xn is equal to n lambda d by d. So fifth bright will be 5 lambda d by d. For dark fringe, xn is given by 2n minus 1 lambda d by 2d. So d2 will be 2 into 2 minus 1 by 2 lambda d by 2d. So if you solve it, it will be 2 to the 4, 3 by 2 lambda d by d. According to question, x5 minus x2 is 4.13 into 10 to the power minus 3 meter. So x5 is 5 lambda d by d and x2 is 3 by 2 lambda d by d is equal to 4.13 10 to the power minus 3. Now we take lambda d by d common, so it will be 5 minus 3 by 2, which is 4.13 10 to the power minus 3 meter. So if you solve it, 2 5s are 10, 7 by 2. So it will come out to be lambda d by d, 2 5s are 10 into 7 by 2 equal to 4.13 10 to the power minus 3. Now we put the values. Lambda will be equal to 2 will get cross multiplied, 7 will get divided, small d will get multiplied, capital D will get divided. So it comes out to be 2 into 4.13 into 10 power minus 3. Small d is 5 into 10 power minus 4, and capital D is 7 into capital D is 1 meter. So if you cut, if you just divide by 7, 7 5s are 35. You are left with 6, 7 9s are 63. So 0.59, and 5 into 2 is 10. So it comes out to be 0.59 into 10 to the power 7, 10 power minus 6 meter. So which is 5.9 into 10 power minus 7 meter. So the wavelength of the light used is 5.9 into 10 power minus 7 meter. So see, by using the concept of where the bright and dark fringes are formed, you can find the difference and hence the wavelength of the light used. Yes, so if I just lower it slightly, yeah, so the wavelength of the light used is this, 5.9 into 10 power minus 7 meter. So in this question, this is diffraction based question. It says two wavelengths of sodium 590 nanometer and 596 nanometers are used in turn to study the diffraction taking place at single slit. The slit width is 2 into 10 power minus 4 meter. The screen distance is 1.5 meter, and what we need to find out the separation between the first maximum formed on the screen due to the two sources. So the distance of the first maximum due to 590 nanometer and due to 596 nanometer, that we need to find out. Now distance of the first maximum is given by 2n minus 1 lambda d by 2d. So in the first case, x1 590 nanometer is given by 2 into 2 minus 1. Sorry, 2n plus 1, so it will be 2 into 1 plus 1 lambda d by 2d, so it is 3 by 2 lambda d by 2d, and in the second case it is also 3 by 2 lambda d by 2d. Now let's put the values. 3 by 4 590 into the screen distance is 1.5 meter divided by, so let it be lambda 1 and this is lambda 2, so that separation will be x1 596 minus x1 590, so it will be 3 by 2 d by 2d lambda 2 minus lambda 1, so it is 3 by 4 d by d, lambda 2 is 596 minus 590 nanometer means 10 to minus 9 meter. So it comes out to be 3 by 4, 1.5 divided by d is 2 into 10 power minus 4 into 6 into 10 power minus 9 meter. If we simplify it 3, it will be 3 3s are 9, 15 9s are 105, so it will be 10.5 divided 4 into 10 power minus 5. So if you solve it, 4 2s are 8, 2, 4 6 are 24, 2 5 into 10 power minus 5 meter. So this is the separation, this is the required separation between the first maxima of the two sources. So in this problem, ultraviolet radiation of wavelength 300 nanometer from a 100-watt mercury source irradiates a photocell made up of metallic surface. If the stopping potential is 1.5 volt for the ejected electrons, so it is case of photoelectric effect. Incoming radiation is ejecting electron with stopping potential of 1.5 volt. We need to find the work function of the metal in electrovolt, the number of photoelectrons, and de Broglie wavelength of the ejected electrons. So let's go to the first part. We know as per photoelectric equation, the photoelectric equation looks like E is equal to phi plus kinetic energy. So E is equal to hc by lambda. Phi is work function. Kinetic energy is equal to stopping potential. So E V naught. So work function will be hc by lambda minus EV naught, which is 6.626 10 power minus 34. C is 3 into 10 power 8. Lambda is 300 nanometer. And E is 1.6 into 10 power minus 19. V naught is 1.5 volt. So this is 100, that means 10 power minus 7. So it will be, it comes out to be 15, 6.626 10 to the power minus 34 plus 15 minus 1.6 into 1.5 will be 9, 15 1 is 15, 9, 24. So it will be 2.4 into 10 power minus 19. Now if you solve this, it will be 6.626 into 10 power minus 19, 2.4 10 power minus 19. So it comes out to be, to subtract 6 to 2, 4, the 10 power minus 19 joules. So this is the work function. Now we have to find work function in electron volts. So this much joule. So in electron volts, phi will be 4.226 10 power minus 19 divided by 1.6 into 10 power minus 19 electron volt. Since 1 electron volt is equal to 1.6 into 10 power minus 19 joule. So this gets cancelled. We have 16 2 is 32, 10, 16 6 are 96, 6, 16 4 is 6, 64 electron volts. So work function is approximately 2.64 electron volt. So this is first part of the solution. Now we come to the second part, number of photoelectrons emitted per second. So uh, we have 100-watt energy. Yes, so this source is 100-watt source and it emits 300 nanometer uh, photons. So number of photons emitted, number of photons emitted per second, m is equal to power divided by energy of photon. Power is 100-watt divided by energy is hc by lambda. So it is 100 divided by 6.626 10 power minus 34, 3 into 10 power 8 divided by lambda is 300 nanometer, 310 power minus 9. So this gives you 100 into 310 power minus 9, and this is 2 into 10 power minus 25. So it comes down to 2 to 10 power minus 5, 20. So 1.5 into 10 power, this is 9, 9, 4 minus 5, 20, 24. So number of photons emitted per second is 1.5 10 power minus 20 photons. Third is to find de Broglie wavelength. De Broglie wavelength will be lambda will be 1.227 by square root of V naught a nanometer. So it is 1.227 divided by square root of 1.5 in nanometer. So the value um, of square root of 1.5 can be calculated, and the final answer can be found out. So square root of 1.5. So it comes out to be approximately 1.002 10 power minus 9 meter. So this is the de Broglie wavelength. So we used photoelectric effect as well as the de Broglie wavelength to find the wavelength of the electrons. So the next set of important questions are, like, from this graph we have to explain which two sources have same frequency and same intensity. So you see this graph is between photoelectric current and stopping potential. The just the potentials, photoelectric current and potential. So you see the sources A and B has got same stopping potential. The graph is between current and stopping potential. You see A and B has got same stopping potential. Now the sources A and B have same stopping potential, that means A and B have the same frequency. Now sources B and C, B and C have got same saturation current, that means they have got same intensity. All right. Now in this question it says that an electron in an orbit has 15 kilojoule of kinetic energy. The electron is an atom. An electron in an atomic orbit has plus 15 kilojoule of kinetic energy. Find its potential energy and total energy. So we know that kinetic energy is equal to potential and total energy, but just the sign is negative. So total energy is minus 15 kilojoule, and since potential energy is twice of the kinetic energy with negative sign, so potential energy will be minus 30 kilojoule. Now this question is about binding energy. It says we need to find binding energy of calcium nucleus. Mass of calcium nuclei is given, separate mass of proton and neutron is given. So first we need to find out the mass defect, that is separate individual sum of the masses of protons and neutrons, and then subtract it from the mass of the nuclei. So if we do this, mass defect comes out to be 0.367211 AMU. Now one atomic mass unit is approximately equal to 931 mega electron volt. So if after multiplication the binding energy comes out to be 341.87 mega electron volt. Now binding energy per nucleon will be, if you divide this binding energy by 40, we get binding energy of 8.547 mega electron volt. So that's we have from this question. Now we can also explain binding energy per nucleon graph. This binding energy per nucleon graph looks like this. So here this is atomic mass and this is binding energy. This is EBN, that means binding energy per nucleon. So iron has got highest binding energy. Now these are lighter nuclei and these are heavier nuclei. This graph shows that heavier nuclei, see, binding energy remains almost constant for heavier nuclei, which means nuclear force is a short range force. And these nuclei will undergo fission because they want to achieve higher binding energy. So these are good candidate for fission reaction and these are good candidate for fusion reaction. So they try to achieve higher by get clubbing together and they want to break down. So these undergo fission and those undergo fusion. So next set of question which is important is write down the differences between fission and fusion reaction. So we have fission on one side and fusion on the other side. So fission reaction, in fission what happens, heavier nuclei breaks down to form lighter nuclei. Like heavier uranium 235 is broken down by collision of a neutron and it breaks down to barium and krypton and three other neutrons gets released. Whereas in fusion, lighter nuclei fuse together to form heavier nuclei. So four hydrogen nuclei are fusing together to give you helium nuclei, slightly heavier. Two neutrinos and six photons are released along with 26.7 mega electron volts of energy. Now, in fission reaction, byproducts are radioactive. See, barium and krypton are still radioactive, and their disposal is very problematic. So, it is not a clean fuel. Whereas byproduct in this case, the helium is very clean and very useful byproduct. Now, this requires fission. The advantage with fission is that it requires relatively moderate condition as compared to fusion. Fusion requires star-like condition, like sun-like condition, very high temperature and very high pressure. So India is trying to build fusion reactor. China claims that it has already built. So people are trying to switch to fusion. Next question is show biasing of forward and the reverse bias in a PN junction diode. In a PN junction diode, uh, also plot the graph to show IV characteristics. You see, if positive terminal is connected to P and negative terminal is connected to N, so the circuit will be forward biased, and if positive is connected to N and negative to P, it will be reverse biased. In forward bias, you see there is sharp pickup, current picks up just before 1 volt, and this is forward bias, and the diode is said to be in on state and current flows in milliampere. While in reverse bias, even after applying 100 volt, you need to apply very high voltage, then also current is approximately 0, it is in microampere. At very high potential, the device just breaks down and then a very large current will flow. So diode can be considered in off state in reverse bias. Next question, it says find the input resistance of the diode. From the graph, you know, at two different potentials you have two different currents. So using Ohm's law, the resistance will be change in potential by change in current. So V2 minus V1 by I2 minus I1. So you just find out V2 is 1 volt, V1 is 0.8, I2 is 50, I1 is 30. So you solve it, you get 10 to the power minus 2 ohm. So input resistance of, of diode in this case is 10 to the power minus 2 ohms. Next question says, what is a rectifier? Explain working of full wave rectifier. So a rectifier is a device to convert AC to DC. A device to convert input AC to output DC. Now a full wave rectifier, so we'll see full wave rectifier. What is full wave rectifier? There is input AC and you have inductive coil. So this is input and there will be another coil to which the flux will get induced. You put soft iron core and you put two diodes there will be a tapping wire, it will be jumped to ground. Now the output will be taken across this ground and these two combination of these two diodes. So this is diode 1, this is diode 2. The output, this is load resistance, and the output is taken. Now when positive waveform comes here, so this becomes positive, this is negative, this is positive, this is negative. So if this diode p side is connected to positive and n side is connected to negative, this diode gets forward biased. So this diode 1 starts conducting, it is in on state. In forward bias the diode will be in on state, whereas in reverse bias this diode, see, the p side is connected to negative and n side connected to positive. So this diode is off. So for positive half cycle, D1 is on, D2 is off. So the output looks like this. This is input, the output will be positive. For negative cycle, this will be negative, positive, negative, positive. The diode 1 gets reverse biased because P is connected to negative, and this diode gets forward biased. So D2 conducts, its D2 is on, D1 is off. So for negative cycle, the output will again be positive. So you see, then again you get positive cycle, then it will be positive. For negative cycle, D2 will conduct positive. So you get constant positive output. So your output is always positive and it is DC output. Now you see this output is quite bumpy. So to make it smooth, what you do, you add a capacitor in parallel. So due to charging and discharging cycle of capacitor, the output becomes smooth. So you get a smooth DC output. So this is smooth DC output. So this shows the working of a full wave rectifier. What we do here, we rectify both the cycle, plus and minus cycle of the input signal. So guys, these were few very important questions which we discussed, which may turn up tomorrow in your board exam. So I hope you enjoyed this session, and if you liked it, please like and subscribe, and also share it among your friends. And I wish you all the best for your exam, guys. In exam, you should keep your cool and just give your best.